So this is, as mentioned earlier, this is a project that's been kind of intensively going for the last 5 months at the Turing Institute. And the names here are the people involved at the Turing, but there are many others. It's an open source project. It has some history before this sort of intensive phase as well, with quite a few contributors. But and these are the ones at the Turing at the moment who are involved. And I'm Anthony, and Franz is not here, but both Sebastian and Janis are here. There you go. Sebastian's put his hand up, and Janis is way over there. So I actually work for an institute in New Zealand, so I'll just mention that. And now to the talk. So what exactly is MLJ? Well, it's what I will call a machine learning toolbox. And permit me to say a few words explaining those words, machine learning toolbox. Of course, it's written in Julia, otherwise we wouldn't be here. So machine learning, as probably most people have gathered, is all about finding some kind of structure or pattern in data, with the idea that you can use that to respond to new data in some way, usually in an automatic kind of fashion. So that's quite a general description. And there are lots of examples of machine learning tasks. This is just kind of a random selection of what we call supervised learning tasks, which are kind of the main front-running type tasks that machine learning is concerned with. So if you're doing any kind of predictive modeling, then you can think of that as machine learning. For example, we can look at credit scoring here. So in credit scoring, maybe you have a database of customers, and you know various things about your customers: their age, their name, their salary, where they live, and so on. And you'd like to extract from that a measure of their risk in terms of giving them a loan. Now, your machine learning algorithm isn't going to do this just in a vacuum. You're going to already have experts providing their own credit ratings, and you're going to use that to train your machine. If you like, the domain experts are supervising the training of your machine. The other kind of task in machine learning is known as unsupervised learning. A simple example of that is, or a familiar example is, if you boot up your favorite photo application, then you'll notice that nowadays your photos get classified into groups where all the people, the individuals that appear in a photos are grouped together. So all the pictures of your father and you can identify them as one group and so on. And this happens without the software actually knowing what the actual names of those people are, right? So he doesn't know who's Anthony or Sebastian or whatever. The photos are unlabeled. And so that's an example of an unsupervised learning task. Another example that may be familiar is market segmentation. So you may have a database, your company may have a database of customers, and it's too complicated to try and tailor your marketing to every single customer. So you want to simplify your marketing strategy by clustering together the different individuals in your database. And so that's an example of unsupervised learning. It's kind of a special case of what is called in the field dimension reduction. So you've got lots of variables, too many variables for your predicting your supervised learning task, for example, to handle. So you want to reduce the number of variables. So that's what unsupervised learning is another example of that. So I would like to give you, you don't need to know much about machine learning to have a reasonable kind of mental modeling of how it works. So let me just give you spend a few moments providing that for the people who are not so familiar. So suppose we are measuring the temperature with a thermometer in our house or wherever, and we're just taking measurements on the hour, and we're automatically recording those measurements. And then someone comes along to you and they say, well, I want to know what the temperature was at 10:43 a.m., which is not a time on the hour. So how might you go about doing that? Well, one thing you can do is you can take the measurements, which are here, the pink dots, And you can try and fit some kind of a curve through the data. Once you've got this continuous curve, you can go to any time of day that you like, right? Say here, you can go up to the blue curve and read off a prediction for the temperature. Now, in general, your prediction may not represent what the true temperature was. So to evaluate how good your model is, you're going to hold back some data. So we might imagine that we were actually measuring the data every half an hour instead of every hour. So then we can go and actually check and see what the predictions of our fitted curve, how well they do. So the first point I want to make in this example is that philosophically, if you look at any kind of supervised learning task, then no matter how kind of mysterious a given bit of artificial intelligence might appear, how magical it might appear to you, morally speaking, it really is just a curve fitting. That is what's going on underneath the hood. Now, the curve might actually be some kind of surface in 100 dimensions or whatever, so there are complications. But morally speaking, that's all a lot of machine learning is. It's just kind of fancy curve fitting. The second point I want to make before we move on is that there are choices. I mean, we haven't actually talked about how we get this blue curve, right? So we're fitting a curve. Machine learning does this for you. And I'm not going to tell you exactly how we might go about doing that. But the point is that there are choices. And, one thing we could have done, instead of trying to draw a curve that looked reasonable through this data, we could have just taken an average of the temperature right throughout the day and said, well, that's my prediction for any time. So that would be like fitting a horizontal line to our data, like here on the right. And as you can imagine, probably for this kind of example, the errors that you get aren't going to be so, the performance isn't going to be that great. At the other extreme, you can say, well, I'm going to fit a 24-degree polynomial to my data. I'm doing a great job. I've got my curve is actually going through every single data point. Well, if we understand that there's some kind of random component to the measurement of temperature, which is more than likely the case, then we can see a danger here in that what we're really doing here with this fancy model is we're fitting to the noise more than we're fitting, as much as we're fitting to the trend. And in that case, that extreme case as well, you may have worse performance than you could have by not being so ambitious. So when we have machine learning models, there are choices to be made, and that means we have, if you like, knobs to turn on our models. So different parameters that we're going to tune, which might increase or decrease the complexity of the model, for example, to optimize our performance. So that's the other thing, that this idea of tuning our models is a very important part of machine learning. Okay, so as I've sort of hinted at, there are lots and lots of different models that you might want to try out in any particular machine learning task. This diagram here is a picture of some of the packages currently written in Julia. It's a little bit out of date, but gives you an idea, that implement models. So, for example, over here we have Flux, which probably a lot of you will have heard about, which implement so-called neural network models. There's a package over here called Decision Tree, which allows you to implement so-called decision tree or ensembles of decision tree type algorithms and so on. And then you have more traditional things like ordinary regression. So the point is that you don't have all models just sitting in one package. They are scattered all over the place, and each package will have its own way of you interacting with the model, own way of fitting the model to the data, own way of tuning those parameters, and so forth. And so that's where the role of toolboxes come in. That's what a toolbox is going to do for you in the first instance. So any machine learning toolbox is going to give you a way to, giving you a uniform interface for fitting, evaluating, and tuning the models across multiple packages or multiple sources. Usually it will also do further things for you. It will perform common pre-processing tasks, like cleaning your data or coercing data types. And it'll provide some sort of pipelining which allows you to compose these different operations, the pre-processing and maybe some of this unsupervised learning, the dimension reduction I talked about. you might want to do that first, and then once the number of variables is decreased, then you go ahead and train your predictive model. So these are the basics that any machine learning toolbox is going to provide. But of course we want to do more than just the basics. So what are the other things we'd like to do? Well, I'm particularly interested in toolboxes that allow you to combine models in more flexible ways. So the existing toolboxes provide generally some kind of way of pipelining, but they're somewhat restrictive. And I think if we want to get creative about the ways in which we blend the predictions of different models and the way we combine them and so on, it would be useful to have a more flexible kind of way of doing that. And I even think the word pipeline is suggestive of a kind of a linear thing. And what we really want to move away from that idea and just do more crazy, more interesting things. Another thing we'd like to do is avoid the redundancies in retraining a learning network or pipeline. So sometimes you might have different parts in your pipeline, you connect them all together, and then you make a change in one of the components of the pipeline that may not actually affect things upstream of it, but typically you have to kind of run the whole pipeline, or may have to run many parts of the pipeline all through, even though it's not necessary. So your pipelines want to be cleverer than that. And another thing is that when you're doing this tuning, you don't want to just do it in a kind of with your bare hands. You want to make that a systematic operation. So if you like, so you want to do that in a systematic way. Just say, well, here are all the parameters that I want to play with, and they may be distributed across different models within a network. They may not all land inside one particular model, and you want to just say, these are the ranges of values I'm interested in, and you throw that to the toolbox, and it'll go away and tune all those parameters for you. Some of these parameters might be nested because you've got models within models and so on. So you want to be able to handle that. Another neat thing which isn't always implemented is this idea of implementing your tuning as a kind of model wrapper, which means you can kind of think of the new model as something that tunes itself, which is kind of a nice idea for composing tuning with other operations. And lastly, I think a nice feature that isn't always in toolboxes is what we call a task interface, where you match the models to the particular data and objectives that you might have, rather than having to scrape through documentation and have a sufficiently good understanding of the different models to find the model that works for your data. This is automated for you to some extent. All right, so I claim that our project, our software MLJ, actually is a toolbox that does all this now. So all those things I've talked about pretty much are already implemented. What we don't have so much of is actually models yet that are implementing our interface, but I'll come back to that later. But we have a lot of features there. Now, I'm not going to talk about all those things, but I want to focus on one, which is this idea of having a flexible way to combine different models together. And for that, I'm going to talk about an example of stacking. So you don't need to know what that is. I'm going to explain it. I'm not going to explain in detail, but give you the basic idea. So so this is the kind of thing that you can do in machine learning existing frameworks, but generally it's something that's hardwired. It's not part of the pipelining, the normal pipelining kind of interface. But we would like a pipelining interface that's flexible enough to do this, because this is kind of a little bit complicated problem. So how does it work? So in a two-model stack, you have two different models. I'll call them machine 1 and machine 2. Data flows in from the left, and each of those models are going to give you an independent prediction of the target that you're trying to predict, say the temperature in the room, for the sort of trivial example. Then what happens is those two predictions get concatenated together into a new table, which gets fed into a third model, which is like the judge. And that judge is going to kind of decide how to blend those predictions and give you a final prediction, which hopefully is better than either of the other two, and there's a good chance of that actually being the case. Now, The subtlety in terms of these stats comes in when you train them, because the way information is going to flow in the training phase of building this network is going to be a little different. And that's something that MLJ is going to takes account of, so that it separates those two different networks, if you like. I probably won't say a lot more about this example now, just to give you a bit of a flavour of the kinds of things that we hope that we will do especially well. So there are existing Julia machine learning toolboxes. I didn't count them per se, but I think I've sort of somewhat reviewed, maybe not a dozen, but 9 or 10 different things that are in some sense a Julia toolbox. Most of them are experimental, and a lot of them are not being sort of maintained. But there are a few that I think I should mention, definitely mention. The first one is scikit-learn, which is actually a Python package. It's a Python machine learning toolbox, and anyone who is doing machine learning will be very familiar with this package. It's a very popular package. So there exists a wrap of that package in Julia already. So, and that's essentially what it is. So it's not really written in Julia. It wraps Julia code, and the extra functionality of a toolbox that I'm talking about, it's not written in Julia. It's just wrapped Python code. The advantage of this scikit-learn is that this is wrapping a very mature toolbox, and by using scikit-learn, you have access to a very large number of models, a larger number than you would in any other way at present. But it's Julia wrapping Python wrapping C, which I think which has all the problems of having more than one language, and so we would like to. MLJ hopes to be able to, in the longer term, have that kind of be able to do the same kind of thing there, but smarter and better. Another model. We actually have a FAQ on the website if you actually really want to see a detailed comparison of the two, because we get asked that quite a bit. Another toolbox I thought is worth mentioning is something called Combine ML. It's got a fair number of the features that you'd like implemented. It at present does what we call classification, but doesn't do regression. So they're kind of two kinds of predicting discrete things or continuous things. But it's a nice package, and I think there is some efforts to keep it being developed, and it would have the advantage over our project in that I think it is simpler, but probably in the long term less powerful, but definitely worth mentioning. And then the last package I should definitely mention, although it isn't strictly speaking a toolbox, is Flux, which is one of the Julia packages for doing deep learning. So Flux is important because it gives you access to not a way of training just any old supervising learning model, but all the deep learning, all the neural network models that are very popular. So definitely worth mentioning, and it's a very nice package. And we have ambitions to kind of integrate that package with what we're doing too. So I think there are some other things that we would like to implement in the short. Oh, here's some other things I haven't talked about, in addition to the features I've talked about. We've tried to make the interface friendly to people who want to do probabilistic type prediction. So I don't want to predict if it's going to rain tomorrow or not. I want to predict what's the chance of it going to be raining tomorrow. So that's an example of probabilistic prediction. Current models don't always do that very well. Current toolboxes don't always do that so well, so we're trying to make that look nicer. Currently, you can also present your data in many different formats, basically anything supported by the tables.jl interface, if you know what that is. And we pay particular attention to categorical data types by implementing them. So we have a universal adoption of categorical data types for dealing with categorical data. We plan to integrate deep learning, and in particular we're interested in doing something called gradient descent tuning of parameters. So gradient descent is a method for fitting models, but you can also use it to tune the hyperparameters of models, provided that you have a way of differentiating a model. So The idea is you use auto-differentiation, but to do that you need to be able to get inside the model. If you've got multiple languages, you can't do that. But in Julia, you can do that. So you might be able to, there are possibilities for doing fancier kinds of tuning in Julia that you wouldn't be able to do with current multi-language setup. And I'm not going to go through probably other enhancements right now. And I'm going to finish with a sort of a small demo. But before I do that, I just want to say that we are looking for help. In particular, we're looking for the following things. We would like, we're looking for end users, so applied machine learning projects to help drive further development. We're always looking for new models to implement. So if you're working on a model, a machine learning model in Julia, we're keen to help you implement our interface for your model. And we're also may be interested in finding more. We're always interested in contributors, but there may even be opportunities for paid contributions if we are fortunate enough to continue our funding. Okay, so I guess I'll just move over to the demo, or we could pause and have questions. What does the AVIC suggest? Should we have questions and then a demo? Demo first? All right, let's do a demo then. Okay, so of course I've done the usual cheat in Julia of already loading my modules to avoid the infamous Julia pause. So first thing to do is we load it, boot up MLJ, and I'm also going to use data frames and some plotting packages. And the first thing I'm going to do is load a task that just happens to be built into the package for convenience, which is the famous Boston data set. Now, a task is a little bit more than data. So a task is data plus a learning objective. So, for example, your learning objective, I mean, your data might be this Boston data set with various features and the median prices. But then the learning objective would be something like make a probabilistic prediction of the median price based on these list of features, something as simple as that. So it's data plus a learning objective. Here's sort of like what a bit of the data looks like, just so you can see that I'm not just making this up. And the first thing I want to demonstrate is this model, matching models to tasks feature. So all the models that are implemented in MLJ get registered in an external registry. So, and all the metadata about those models is there. So for example, you will know if a given model can support continuous data or categorical data, and you'll know something about the kind of target that can be predicted. So since that's all accessible, you can take a given task and say, what are all the models I could possibly run on that data plus given the learning objective that I have? So you just do that by saying models around your task, and there is the list of models. I think in this case where the task is doing deterministic prediction, not probabilistic. So this is maybe half of the models that would be available to you at present. Once you've got a model that once you decide you want to try one of these models, later you'll be able to do this systematically, but not yet, then you can now load in that model from the package, the external package. So you're not loading all the data at the beginning of the game already. I already did this, so it's not actually doing anything there. And now you've got your model and you instantiate it. So tree is an example of what's called a decision tree, which is a kind of machine learning model. And all that code is doing there is instantiating a struct which has as its fields the hyperparameters of the model, the different things that you can tune. So for example, how deep you make your tree, that max depth, that is a parameter. In this case, there's no bound because it's -1. So so you start with the model, or you start with basically a container, a list of hyperparameters, let's say that. Once you've got that, you can wrap your task, wrap your model with the task that you have, the data, basically. And now you're pretty much, so that's now a task plus model. Now you can already immediately evaluate that model according to some strategy. So what's this strategy? This is this resampling strategy. It says here that to evaluate the model, I'm going to hold out 80% of the data. And then you get, and you also can specify how you're going to evaluate it, what sort of a measure. So here there's what this RMS is, this root mean squared, and then you have this other measure as well, and they both get spat out. Now we can do one step more complicated. We can construct an ensemble of models. So here's the first kind of way that you can combine models. So you've got your decision tree, and instead of just having a single decision tree making decisions about, that you're going to train, you take one decision tree and you train it on almost all the data, some random subsample of the data, but not all of it. Then you take a second tree, you train it on a different random subset of the data, and so on, and maybe you take 100 trees or 1,000 trees, and they're all a little bit different because of that random sampling of the data, and you take a average of their predictions. So that's an example of an ensembling method. And you can do that with any model in Julia. It doesn't have to be a tree. So in the case of trees, you get what's called a random forest. So I'm calling this random forest. And that's just another model, like the first one, except it has some new interesting features. The most important one I'm going to focus on is just the number of trees that you're actually going to use. And you don't want to run too many because it takes a long time, but you want to have an idea that you're running enough that you get some sort of convergence. So we can test this by building what's called a learning curve, plotting a learning curve. So maybe I'll just skip to that. So I wrap my model in data, and then I choose a range for this number of trees, going from 10 to 500, and I can generate a bunch of curves and plot them. And there you see that after 200 or 300 trees, I'm pretty much settled down. So I'm just going to set the number of trees to 20 to save time. So here's my model. You can look at in more detail to see that it really is what we call a composite model, because here we've got one of the parameters, one of the hyperparameters of our model is atom is actually another model, namely the tree. So we have this idea of nested parameters I was talking about before. And now the next step is to tune our model. So our model, which is now a composite model. And I'm going to, just for demonstration, and this will be pretty much the last thing I do, I'm going to pick two parameters to tune at the same time. One is going to be something called the number of sub-features, which is particular to the tree. I'm not going to explain what that is, but it's a parameter, a common parameter that's used in tuning. And the other parameter is going to be is what's called the bagging fraction, which is how much of the data I'm resampling to get each new copy of the atom, of the atomic model. So I specify the ranges for those two things. I combine that into a single object called nested ranges. And now I'm ready to tune my model, or to more precisely wrap my model in a tuning strategy. So you specify a tuning strategy, a grid strategy, which just means you sort of search over a big grid specified by those ranges. You say how you're going to do the resampling, in this case what we call cross-validation. Some of you know what that is. And then we are ready to specify a new model, which is now a third layer. So we started with the atomic model, then we made that into an ensemble, and now we're wrapping a tuning strategy around that. And so we can now think of this thing as a self-tuning random forest or ensemble model. And we can evaluate it just like we did before. And what's going on here is kind of interesting because there's nested resampling happening here, because there's resampling happening for the tuning, and then there's resampling happening for the evaluation. So that's kind of neat. And you can inspect the results of the tuning to see what's the best model and so on. And you can even generate a plot to show how the tuning went. So in this plot here, we've got the two parameters we were tuning, and the darker the colour, the better the performance. I think it goes like that. Yeah. So you can maybe get an idea of where you should focus, do your fine tuning, that kind of thing. So these are all typical tasks that you do in machine learning. And I think that's probably all I'm going to say on MLJ for now. So thanks for your attention.
Thank you for the talk. I kind of have two questions, actually. So the first one is you mentioned in the future using gradients to tune hyperparameters.
Yeah.
So the first question is, what's your current strategy for sort of implementing automatic differentiation in the package? Are you going to use Flux?
Well, that's our hope is that that we'll be able to use Flux to do that. So at the moment, it's not me. There seem to be maybe some problems, which is that how do you mark the parameters that you actually want to differentiate? At the moment in Flux, you kind of have to wrap them as these tracked arrays, right? But but I understand that there's progress in Flux to make that to improve that, and I'm hoping that might be allow us to do this. But it's still it is somewhat speculative. I can't say definitely we're going to be able to do it, but the hope is that we will be able to do it.
Okay, maybe when Zigga is released.
Exactly. Yeah.
The second question was, apart from gradient-based optimization, do you have plans for Bayesian optimization for hyperparameters?
We're open to implementing in different kinds of tuning strategies. You're the Bayesian expert. Do you see any reason why we can't implement the Bayesian optimization?
No, it's just method presentation at the moment.
Yeah.
Okay, cool.
Certainly, anyone who has wishes for this project, you can go ahead and open an issue and just say, I want this. And it doesn't mean it'll get done tomorrow, but it means it's on our list. Yeah. Did I answer your questions?
Yes.
Okay. Any other questions?
So you showed how we could do this thing where you give it a task, it tells you what kind of models are good.
Yeah.
I was wondering if you can do the same thing for measures. So like you can't use the same measures to evaluate regressionist classification.
There'll be a check to sit. So at the moment, that will definitely. I'm not sure that is implemented at the moment. So you could ask it to evaluate performance using a nonsensical metric at the moment, but certainly that would be a reasonably high priority to have some kind of checks. What is implemented already is that there's a mechanism for choosing a default metric. So one thing that we do, I haven't talked much about here, is we kind of have a distinction between machine types of data like float or integer or whatever, and scientific data types. And so that kind of it's just a nice way of organizing the models, but also doing things like you suggest, is matching metrics to particular models. Yeah.
In your grid search,
Yes.
you could specify a lower and an upper for the ranges. Do you sort of do a rough search and then gradually home in on the best value for the parameters?
So at the moment, what's implemented is simply you specify the range and then a resolution as well. So, and you have to, if you want to go have a finer resolution or you want to search in a different space, you have to do that by hand. But a more complicated. There's no reason why we couldn't implement a more something along the lines you suggest. But we haven't thought about doing that in the near future. I mean, there are so-called genetic algorithms for doing search, which are popular among some people. That seems like something we might want to do pretty soon. Or just random search is another thing we might like to try. Those will probably certainly, hopefully, come soon.
So before we end, let me ask Sebastian to maybe give some idea of the future of MLJ. Sebastian's a professor at Warwick and one of the PIs at the Turing Institute. So Sebastian.
Yes. Sorry. Okay. Sorry. So yeah, thank you, Anthony. Thank you very much for the talk. So we are very grateful at the moment to have there's a toolbox and systems program at the Turing, which I'm not representing, but which is funding the current work which we're doing, and we're looking to apply for a second round of funding, which really requires us which is a good thing, to work with end users, particular end users in the areas of health, data science for science, criminal justice, urban analytics, or data-centric engineering, which is quite broad. But so we're still there's a lot of basic things we need to improve. But in order to get the second round of funding, we are looking at different broad directions in order to implement big features. So be it around, say, fairness metrics, if we were to work with the end user in criminal justice, or be it around, say, anomaly detection methodology, if it's maybe some data science for science experimental data where you need to spot some unexplainable pattern. And so if there are in the room some people that work in that area, or that want to potentially, when we do this application for further funding, that means we can maybe have around 3 full-time staff as opposed to 1.5 at the moment on the project. So if you're interested in either helping us with the end user engagement or helping us with potential manpower because you're interested in this project, just approach us after the talks. Thank you.
Thanks, thanks, Sebastian. So yeah, if all of this sounds interesting to you, please reach out to Sebastian now or later.